Okay, so let's start talking about the ideal gas law. So far, we've looked at the behavior of gases and the way we can define that mathematically using Boyle's law, Charles' law, and Avogadro's law, and then combining those together if we have an initial and final set of conditions. What we haven't looked at is how we can define any one of those variables for an instantaneous situation of a gas. A lot of the times when we're doing things, we won't necessarily know our final and initial set of conditions, so we need to be able to calculate what's going on in a system at one particular time. And to do that, we're going to use the ideal gas law. Okay, so this is just a review of the laws that we've looked at. Okay, so we have Boyle's law being inversely proportional to pressure, the relationship between pressure and volume, inverse. Charles's law, our direct proportional relationship between volume and temperature, where temperature must be in the Kelvin scale. And our relationship between pressure and temperature, that also holds where our temperature is only in the Kelvin scale, not the Celsius scale. And then the combined law of P1V1 T1N1 is equal to P2V2 T2N2 as each of our individual gas laws. So we talked about at the end of the last video how we're going to bring this into equal what is known as the ideal gas law, which is PV equals nRT. And this is an equation that will allow us to find the relationship between pressure, volume, the number of moles, and temperature of a gas at any one particular situation. And in order to do that, we need to have R, this value here, our gas constant, and we need to define this. This equation is actually given in your data booklet, as is the value for R. Okay, there are different values of R. We only use one. So if we look at the mass and therefore the mole of gas, as this varies, the combined gas relationship can be PV equals a constant multiplied by the number of mole and the temperature. This constant can be replaced with the gas constant or the universal gas constant, and then we get PV equals nRT. This equation is only true for real gases, so the solutions that it gives are based on the assumption that our gas is acting ideally, which means that any solution we get for this, when compared to a laboratory value, it may differ for a real gas. But essentially, we don't have an equation that works all the time for a real gas, so we assume that gases are acting ideally every time that we use this. Okay, and as I mentioned before, R has a value that depends on the units for pressure and volume. So you need to be very careful if you're doing extra research on this on the internet or in other textbooks. There is another value that is commonly used, which uses atmospheres for pressure. Okay, whereas for IB, we are looking at only dealing with pressure in pascals and kilopascals. Okay, so the value of R that we use is related to that unit of pressure. So that value is 8.31 joules per Kelvin per mole. Now we set, so this is the amount of energy per Kelvin per mole. Okay, and this value is only true when our P substituted into PV equals nRT, our P must be in kPa. So a lot of the values for pressure that we've looked at were in PA, which is pascals. Okay, and just with any metric conversion, in order to go from pascals to kilopascals, we're going to divide by 1000. To go from kilopascals to pascals, we're going to multiply by 1000, okay? That kilo in a unit is equal to 1000. Okay, so kilo going to kilograms, we multiply grams, we need to divide by 1000. Okay, so when we go to the larger value from the smaller value, we need to divide by 1000. When we go from the larger value to the smaller value, as in kilopascals to pascals, we multiply by 1000. Okay, and this graphic here actually mentions a number of the different gas units that we can see, which is atmospheres, millimeters of mercury, torr, pascals, kilopascals, bar. Then we've got newtons per meter squared, Okay, so essentially we are dealing primarily with these ones, pascals and kilopascals. Okay, here it says 101.325. The SI is just 100, and we'll talk about that later. So our pressure must be in kilopascals. Volume, like everything else in the IB, is going to be in decimeters cubed. So we need to convert that if we need to. And temperature must always be in Kelvin. Remembering that to go from degrees C to Kelvin, we add 273. Okay, so we need to always pay attention to the variables that are changing and also the units that we use for those. So remember we said with the combined gas equation we can remove whatever is constant at the time. So remember Boyle's law, we had this relationship that P times V will equal a constant if the amount of mole and T are constant. Okay, and then we have this V on T relationship where P and N are constant for Charles, and then this relationship here gives us the combined gas law. So what you can see here is that PV over T is equal to a constant, and if we have a look here, PV on NT, being keeping our number of gas constant as well, is going to equal to the universal gas constant. Okay, so for a fixed amount of gas, we can remove N out of this equation, and PV on T will always equal for the same amount of gas. Just a note on pressure, this gives you some of the conversions. Okay, so we're interested primarily in pascals and kilopascals. Oh, sorry about that. Okay, pascals and kilopascals. Okay, one of the ones that is more commonly used, particularly when you get to university, is atmospheres. Okay, so atmospheres, 1 atmosphere of pressure, 1 ATM, is the pressure at sea level. Okay, so that's actually the pressure we feel pretty much every day. That's the pressure that our atmosphere places upon us just when we're walking around. Okay, so if we are at sea level, it's 1 atmosphere. If we go up much higher, the pressure decreases as we go up because the force of gravity on our atmosphere lessens and our atmosphere is pressuring on us less. But 1 atmosphere is at sea level. So to go from pascals to atmospheres, we divide by 101.325. Divide by 101.325. To go from atmospheres to kilopascals, it's 101.325 that we multiply. Okay, primarily though, you are going to be looking at this one here. Millimeters of mercury is what you will often see barometers, and when we do our prac this week, we will look at a barometer in the lab to measure because it works on the expansion and contraction of mercury. So that one we read from there, and to go from millimeters of mercury to atmospheres, we divide or multiply by 760 depending on which way we go. Okay, and then as you can see here, for most conversions, we always go through atmospheres to get to a different pressure. And but primarily, as I said, the IB exam questions tend to deal with this pascals, kilopascals, and don't tend to ask you to convert units too much, but it is worth being aware of. So let's have a look at some questions using PV equals nRT. So for these ones, we are not having an initial and a final. We've got a single situation and we need to work out what's happening with our gas. So let's have a look at what the values of the question are giving us and see what we can find out. So we are asked to calculate the amount of oxygen gas, which anytime we've got amount, that's going to be N, in a cylinder of 30 litres. So for us, that's 30 decimeters cubed. Okay, if the pressure is 20 atmospheres. So 20 atmospheres. Okay, and to get from atmospheres to kilopascals, I'm going to multiply by 100 because this is the value that's in your data booklet. Okay, so normally I would use 101.325, but this is the updated SI as 100 kilopascals. And to go from atmospheres to kilopascals, I'm going to multiply by 100. So, and we have 30 degrees C, so this is my temperature, and that means I have to add 273 to it to get it into Kelvin, which is going to be 303 Kelvin. Okay, so what we want to do here is use our PV equals nRT. We have been asked to find the number of mole, or the amount of oxygen gas, so we're going to look for N. So I'm going to rearrange my equation, and I'm going to bring R and T over to the other side. So PV divided by RT is going to give me my number of mole. So let's substitute in. So 20 and then multiplied by 100 is my P, multiplied by my volume, which is 30, all over RT, remembering R from our data book is 8.31 joules per Kelvin per mole. Okay, so in this case, we're going to put 8.31, remembering that our denominator needs to go into brackets, 8.31, and then multiplied by 303. So we can just put that into our calculator. Sorry about the slide change there. So 2000 multiplied by 30, and then we're going to divide that by 8.31 multiplied by 303, and we should get 23.8290. Okay, and we're going to look at our significant figures here. We have 303 here, we've got 30, so we want two significant figures. Okay, so in this case it would be 24 mole. Note that I am leaving my unrounded value here so that my examiner can see what I've decided to do with my rounding. So in this case, we would have 24 mole will occupy 30 litres at a pressure of 20 atmospheres and 30 degrees C. Okay, so as you can see here, we haven't got an initial and a final. We just have that straightforward one situation need to calculate it. This one has another pressure conversion just to show you how they're done. So let's have a look at this one. We have 3.2 grams of helium. So this is a mass, okay, occupy a volume of 25 litres, so 25 decimeters cubed, at a pressure of 700 millimeters of mercury. Now to convert this one, I need to go to atmospheres, and then I need to go to kPa. So to go from millimeters of mercury to atmospheres, I'm going to divide by 760. So 700 divided by 760 is going to give me 0.9210 atmospheres. And then to go from atmospheres to kPa, I'm going to multiply by 100, which when I do that, I'm going to get 92.105 kilopascals. Okay, so that's my pressure worked out. So this is P. I have V. Okay, I want to find T, remembering that it will be in Kelvin. So if PV equals nRT, this time I'm solving for T. So I'm going to get T is equal to PV divided by nR. One catch that we need to realize here is we don't have N. So I need to work out N, and we're told it's helium. So N of helium is going to equal, I've got a mass, 3.2. We're going to use our periodic table. Okay, and we should find that the molar mass of helium is 4 divided by 4. 3.2 divided by 4 is equal to 0.8 mole. So if I have 0.8 mole, I'm now going to substitute that into here, and I'm going to get T is equal to my pressure, which was 92.105, multiplied by my volume, which is 25, all over N, which is 0.8, multiplied by 8.31, which is our gas constant. And we should now see that we can get 92.105 multiplied by 25. Divide that all by 0.8 times 8.31. And we get a value of 346 Kelvin. Okay, so it's 346.36. We can't give Kelvin in any more lower value than this, so we're going to keep to the 3 sig figs and lose my decimal points, which were 0.36. So at 346 Kelvin, this is the temperature that this gas would occupy that volume. Okay, so hopefully that makes a bit of sense. Try some of the questions from your textbook, and then we will move on from there.